name's Jordan Sager. I am a mechanical engineer and also the Associate Director for Facilities Management here at UCSB. So I'm a facilities guy. I'm here to talk about a project that we've been developing for the past several years now that relates to our heating systems on campus, primarily heating electrification. UC Santa Barbara has been engaged in climate action planning and resilience planning for decades, since our first greenhouse gas emissions inventory was completed in 2005, to the partnership with Edison to construct the 66 kV Colegio substation on campus in 2009. We've been working on these issues for some time. University of California, Santa Barbara has the lowest greenhouse gas emissions of any UC in the system. That is due to a number of factors, but one of the big ones is we do not have a fossil fuel burning central plant that generates heat or power. Every other UC in the system does. We've got distributed heating systems, so think natural gas boilers at every one of our major buildings. The UC became classified as an energy service provider about 10 years ago. That means the University of California can develop renewable resources and storage resources off-site. So while we've worked, I'm sure you've seen our solar projects that we've built on this campus and other UC campuses. We've also got the ability to develop and enter into contracts to develop resources really anywhere on the grid and send that power to the campuses. So because the University of California, Santa Barbara gets such a large share of its source energy from electricity, instead of bringing gas to power to campus and burning it to power heat and electricity, we've got the ability to decarbonize our electricity supply entirely. In fact, we did that in 2019. So we've eliminated emissions from electricity on campus. University of California has a policy that says we've got to get to 90% emissions reductions compared to a 2019 baseline by the year 2045. So that's what we're working on now. That's what's led to our Clean Energy Master Plan. So the biggest kind of challenge, the way we see it on campus now, is our natural gas emissions for combustion that does happen on campus, the majority of which is for space heating. So 83% of the natural gas burned and 83% of our operational emissions are from heating buildings. Slightly less than that, 12% is for domestic hot water. We've got laundry and cooking at kind of minor percentages there. So we do a lot of simultaneous heating and cooling on campus, meaning we've got 120 major buildings. Some of them may be heating, some of them may be cooling. Coincidentally, some of them may be doing both, depending on the processes that are going on in those buildings at any given time. In the winter, you can see on the left-hand side, we're heating dominated. So at night, in the early morning hours, most of the energy is going into heating. We've got a little bit of cooling dominated time in the afternoon hours, but that yellow overlapping area there is time when we're doing both on campus somewhere coincidentally. And that's really what we want to get at through this project. In the fall and summer, when it's hot outside, we're cooling dominated, and in the spring, we've got a great deal of overlapping heating and cooling. So how do we get at this simultaneous heating and cooling? The project that we've developed includes construction of a central utility plant that provides all electric heating resources through heat recovery chillers and air source heat pumps. This is a massive project. It's consolidation of all of those distributed natural gas boiler plants into a single plant on the campus that builds electrified heating resources. We can extract heat from our existing campus chilled water loop. We can also extract heat from the ambient air with air source heat pumps. We've got a fairly large thermal energy storage resource as part of this plant as well, both on the hot water and the chilled water side. Those are our batteries, right? So we can generate cooling when it's efficient to do so, charge up our chilled water tanks and discharge them during the 4 to 9 PM period when the grid is constrained, when we see our highest demands. Likewise on the heating side. So it's a $300 million project. So in addition to the central plant, we build a heating hot water distribution network that connects to every major building on the campus. Boiler plants come out, all electric heating source is tied to each building at the tune of about $300 million for the project that we have envisioned. We looked at a number of different technologies to do this. We looked at geothermal, we looked at the ocean as a heat source and sink, our lagoon, different mixes of technologies. At the end of the day, the air source heat pump plant with thermal energy storage was the optimal solution for us. So that $300 million project, day one, has a total life cycle cost over 45 years of about $2.25 billion. So that's a lot to get at the carbon savings that we're talking about here. But when compared to our business as usual, for the equipment replacement costs that we would see over those 45 years, in dark blue, the utility costs that we would see over that time period, in gray, and the operations and maintenance costs in green, we're doing better than our business as usual case by about $750 million. So there's a very compelling economic proposition here, and that's really what this project is built upon. There's a lot more detail to this project. It's all online at energy.ucsb.edu if you're interested in learning more, and I'm looking forward to talking with our breakout group some more about it this afternoon.